Today, we are going to talk about non-terminating systems. So, what is non-terminating system? A non-terminating system is like a manufacturing process where there is no specific condition for terminating or shutting down the system. So, if you consider a manufacturing plant, it continues working every day, maybe let's say 8 hours working day. So, at the end of the day, we just close the door and leave, and we come back tomorrow and start from where we left off the day before. Okay, so at the end of the day, at the end of 8 working hours, we have some working process on the manufacturing plant, some parts that are in the middle of the processing. So we just leave them where they are, we come back tomorrow and continue working on them. So it's not that when we close at the end of the 8 working hours in a day, we continue till we finish all the working processes. Okay, that's not the case. So, and also every morning when we start the system, we are not starting from zero parts in the system, right? We start from where we left off the day before. So if the day before we had, let's say, 10 working process somewhere in the middle of the production process when we left, the next morning we start from having 10 parts somewhere in the middle of the production process, and we just continue the production. Okay, so that's completely opposite of terminating system, where every day we would start with 0 people in the system, and we continue the system till we continue the simulation or the system till everyone is out. Okay, so these two were characteristic of terminating systems. But for non-terminating systems, as I said, there is no specific terminating condition. Every day when the working hours is over, we just stop the system. We don't continue till every working process is out or anything, and then the next day we just start from where we left off the day before. Okay, so that's called non-terminating system. And again, as I said, manufacturing systems are good examples of non-terminating systems. Okay, so to be able to learn how do we simulate non-terminating systems, let's look at this example. So we are going to create a model. The name of this model will be machine manufacturing dash non-terminating systems. Okay, so create a new model, name the model as machine manufacturing dash non-terminating systems. So in this new model, we have jobs that are coming to the system. Our entities are jobs. So we receive one job every 1.175 minutes. So this inter-arrival time is fixed. So we receive one job every 1.175 minutes. The jobs go to pallet 1, which is a queue, then to machine 1, pallet 2, machine 2, pallet 3, machine 3, pallet for machine 4, and then leave the system. So the process is pretty simple. So we just want to learn how to basically capture the non-terminating system nature of the problem. So the processing time on machine 1 is 1 minute exponentially distributed. The processing time on machine 2, 3, and 4 have Weibull distribution with two parameters, alpha equals to 5 and beta equals to 1. So we didn't have the Weibull distribution before as the processing time for the machines or for creating the random variables. So Weibull distribution is very similar to normal distribution. It has bell shape, and depending on the value of the alpha and beta, the bell shape is a little skewed to the right or to the left. Okay, so it's bell shape, but it's not symmetric, not like normal distribution. So it's a little, again, depending on the values of alpha and beta, are a little skewed to the right or to the left. So one other things that we know about these process times on machine 2, 3, and 4 is that they have a minimum time. So processing time at machine 2 is minimum 0.1 minute, but it can be larger, and that extra value comes from this Weibull distribution. It's the same for machine 3 and 4. The minimum time spent on machine 3 and 4 is 0.25 minutes, and the extra time is coming from these Weibull distributions. Weibull distribution generates a random number greater than 0. So that's why. So when they generate something that is greater than 0, that number is added to the minimum 0.1 or minimum 0.25 to guarantee that the processing time in these machines are at least 0.1, 0.25, and 0.25. Okay, so let's create this model in the ProModel. So all the queues have capacity of infinity and the machines have capacity of 1. So make sure your queues are queue and not a palette. Okay, so let's go to ProModel and see how this model has been created. So again, as I said, we create all these locations. We have about 8 locations. So the queues have capacity of infinity, machines have capacity of 1. So just note that for the queues here, I don't have the first in, first out rule. Again, that's not important. It's just, I just mentioned that so that you have the same setup so that our numbers are as close as possible to each other. Okay, you could put first in, first out. That's not the big deal, but again, mine doesn't have, and just make sure yours don't have so that our numbers are close to each other. Okay, so just make sure your queues have capacity of infinity and the machines have capacity of 1. So I have one entity that comes to the system. Those are jobs, and as I said, jobs arrive to the system one at a time every 1.175 minutes. So my only entity is jobs. Okay, and these jobs arrive to the system at they first enter pallet 1 at a time from the start of the simulation every 1.175 minute fixed, and they come to the system for as long as I run the simulation. Okay, so let's go and see how we can model the processes. Again, the product just go through this process through the machines and pallets one at a time, and so the process is also straightforward. So let's go to the processes. Okay, so as you can see here, pallet 1, jobs that are already in pallet 1 go to machine 1, then from machine 1 they go to pallet 2. At machine 1, as I showed you, the processing time is 1 minute exponential distributed. From machine 1, they go to pallet 2, then from pallet 2, they go to machine 2, and then from machine 2, they go to pallet 3. So just make sure that as we showed you guys here on machine 2, processing time has variable distribution alpha 5 and beta 1, and we want the minimum amount of processing time to be 0.1. As I said, variable distribution generates random number greater than 0. So if I want the minimum to be 0.1, I have to say that the processing time or the wait time here is 0.1 plus whatever random number variable distribution will generate for me. So for the variable distribution, we write it as W. The first parameter is alpha and the second parameter is beta. So here our alpha is 5 and beta is 1. So I will write wait W51. And again, if I have a minimum time of 0.1 or 0.25, then the wait time would be wait 0.1 plus this random number that would be generated by the variable distribution. So in this scenario, I will generate a random number from variable distribution with parameter alpha 5 and beta 1. This random number is greater than 0. And then to make sure the processing time is at least 0.1, I will add this random number, whatever it's going to be, to 0.1. So as a result, I'm 100% sure my processing time is greater than 0.1. Okay, so we are going to basically write this wait time for the machine 2. Okay, so wait 0.1 plus variable 5.1 is the processing time of machine 2, and then we go to pallet 3, and then from there we go to from pallet 3 to machine 3, from machine 3 to pallet 4, and then at machine 3 we are going to have variable distribution again with parameters alpha 5 and beta 1, but we want the processing time to be at least 0.25 minute, so the wait time will be 0.25 plus whatever random number variable would generate for me. Okay, and so I'll go to pallet 4, and then from pallet 4 to machine 4, and then finally from machine 4 to exit. Okay, and again at machine 4, again the processing time is 0.25 plus whatever random number variable distribution would generate for me. Okay, so the processes are pretty much simple because again, as I said, the part just goes through these operations palettes and machines one by one, and the variable distribution is not it's not hard at all. We can just write it like any other distribution. Okay, so what I want to do here is also calculate the working process of this manufacturing factory. Okay, to calculate working process, I go to variables, create a global variable, call it working process. And this working process obviously would be integer. And then I come back to, after I create this variable, this global variable working process, I come back to processes and I see, okay, where is the right place to increase working process variable? Obviously, when the parts just get to pallet 1. As soon as they get into the system, they get to pallet 1, I increase working process. And as soon as they are done at machine 4 and they're leaving the system, I decrease working process. Okay, so again, this part is easy too. So we have created and calculated working process variables in different problems many times. So when they get to the system, when we increase working process, and when they are done at machine 4, after the wait time, we decrease working process. Okay, so what I want you guys to do now is to simulate for 250 hours. Okay, so no, nothing. So just simulate this for one replication for 250 hours. So I have created 12,000 jobs. Or 12,000 jobs have left the system in this 250 hours, and the average time in the system is 26 minutes. Okay, so what I want to do now is to create a time plot of the working process. Okay, so let's go to time plot. Okay, so I want to create a time plot. So let's go to time plot. Here as the periodic average, I don't want to have any average or anything. I just want to plot the data, and I'm going to look at it in hours. Okay, and this is my working process. So basically this plots our variable. Okay, so and here if you check the W working process, it just plots your variable for you. Okay, so make sure there is no grouping in plotting the data, and the x-axis is hours. We ran the simulation for 250 hours. That's what we see in our x-axis, and then for the variable, just pick working process. That's the only variable that we have, but make sure that's the one that is checked. Okay, so now let's look at the working process and see how we can make sense of working process here. Okay, so these are values of the working process. That means obviously initially when we started the simulation, there was 0 part in the system. Gradually the number of working process went up and then came down and went up again, and gradually stayed around, like say 27 or so here in this part of the simulation. Okay, so if I ask you guys to report a working process, what model generates is the average of all these numbers that the model generates for working process. Okay, and in this average, it also includes these 0 numbers or small numbers that have been observed right at the very first day of this manufacturing process. Okay, or very first day of this simulation, right? So, however, the fact is that these numbers 0 or these small numbers we have observed here don't happen all the time. So these have happened only at the first couple of days of the simulation, maybe first day or 2 of the simulation. After that, we have gotten to somewhere around 20 something, and we have stayed like that over time. So if you want to report a correct value for the working process, in your average of these numbers, you should not include these initial numbers, these 0 numbers, because they have happened only once in this production process and they never happen again. And they happen only once because That's the start of the simulation, or that's the very first day of the manufacturing process when we really started with 0 part in the system. So for a correct and reliable number for work in process, we don't want to report these numbers that did not happen frequently or at all anymore in the system, right? So in other words, we want to let the work in process variables to go through all its up and downs and then gradually get to an equilibrium point or a steady state. And then when we get to that point, we want to just include these numbers in calculating work in process. So all these initial ups and downs till we finally get to this equilibrium point, I don't want to include them in any calculation. So the system was not really stable yet around this time. So I don't want this time of the simulation to be included in any calculations. When I report work in process, I just want to include these numbers in calculating work in process because these are the numbers that are really representing how the manufacturing process works. Okay, so then the question is that how can I tell simulation to get rid of these initial part of the simulation and do not include them in any calculation? Okay, and how long is this initial part that we do not want to include in any calculation? So let's say about 100 hours. Okay, it can be a little more or a little less, it doesn't matter, because it's just simulation. Just run is really fast for 100 hours and then drop these numbers and then just include the rest of the simulation in the calculation. So how can I tell the simulation to get rid of these first 100 hours and do not include it in any calculations? That happens through warm-up time. So here in the simulation options, when we go through, you see there is an option for warm-up time. So if you check this warm-up period, if you check this, we in any model we have basically did so far, the warm-up period box is unchecked, but if you check it, the warm-up time is calculated. So now I want the simulation to still run for 250 hours, but I want to consider the first 100 as my warm-up time and then the next 150 as my simulation time. So basically I want the simulation to still run for 250 hours, but I don't want to include the first 100 hours in the calculations. That's my warm-up time till I finally get to a steady state, to an equilibrium point in the manufacturing process. So I just want to drop whatever number I get from the simulation in the first 100 hours and just include whatever happens in the next 150 hours in the result, in the reported results. Okay, so that's basically what warm-up time means. How do we know what is the good warm-up time? By picking up some variables, again, similar to work in process or so, and see when your system is starting showing some equilibrium or steady state behavior. So anything before that can be considered in your warm-up time. You can just drop it and consider anything after that as your actual simulation time. Okay, so let's do that. So here again, when we look at the first row, if you remember previously, we were creating about more than 12,000 parts, but right now we see that we are creating about more than 7,000 parts. So the first 5,000 or so were the parts that were generated in the equilibrium time, and then we don't want to include them in the process anymore. And the average time in the system right now is 20 minutes. And if I go to my work in process variable, we see that work in process is about 24 minutes. Okay, so I'm sorry, it's about 24 parts. So for work in process, I look at average number of parts that are in the system. We look at the average column, and that's about 24 parts on average are somewhere in this manufacturing process at any point of time. If I run this one more time without a warm-up time, if I just run it for 250 minutes, you can just inactivate warm-up time or just delete everything. So if I run this one more time for 250 minutes, the original scenario, if I run this and I Go to work in process. You see your working process is 22 minutes, okay? Because it includes all those small numbers that we had at the start of the simulation at time, the first 2 days or so, all these zero values or small values. So that's why the working process is smaller. Now it's 22.59, but as you saw, if I include the first 100 hours in my as my warm-up time and just run the simulation for 150 hours, when we reach to the equilibrium point, the working process has increased a little. So it's now, we see that it's more than 24 minutes. I'm sorry, the working process is more than 24 parts. Okay, so on average, 24 parts. So the number is greater than, is larger just because we got rid of all those small numbers that we had for working process at the start of the simulation. Okay, so basically then for non-terminating system, we should have a warm-up time so that we don't start just from zero and include a bunch of calculations in our results that do not make sense. So we do want to have a warm-up time for pretty much most of the non-terminating systems, and then after we get rid of all the numbers that are created during the warm-up time, then we run the simulation for a specific number of hours, and the simulation reports the results for this runtime. Okay, so the next question that I have from you is that, what if I want to know how much I can produce in 100 hours? Okay, so I want to know how much exit, let's say how much part can be produced and exit the system in 100 hours in this manufacturing setting. Okay, so obviously if I want to do that, I'm going to consider some time as my warm-up time, let's say the first 100 hours, and then I'm going to just run the system for another 100 hours to see how many parts can be produced in this manufacturing setup in 100 hours. Okay, so let me run this. Okay. So what I see here is that about 5,000 jobs are created in this manufacturing setup in 100 hours. Okay, so number of parts that this setup can produce in 100 hours is just about 5,000. Okay, but if your manager asks you to tell him how many jobs can be produced in 100 hours with this setup, you can't just run the simulation once and just produce 5,000, the number 5,000 and number of parts that will be produced, okay? Because that's just one instance, okay? So how we can basically generate or report a number that is more reliable, okay, instead of just running the simulation once for 100 hours or observing the manufacturing process once for 100 hours. You want to repeat this several times and then report the average of all those parts that can produce in 100 hours, assuming that you have been able to repeat these 100 hours several times. Okay, so maybe you go to the manufacturing setup, you observe what's going on in the first 100 hours, you go another time and again observe what is happening in the manufacturing setup in 100 hours. So that gives you 2 data points for how many parts can be produced in a manufacturing setup in 100 hours. So the question is that how we can do that in a non-terminating system. Okay, so basically what we want to do is to see how many parts are produced in a manufacturing setup in 100 hours. So there are 2 ways to be able to do that. So let me just ask you guys which one of them makes more sense. Okay, so obviously one of them is to run the simulation for 100 hours as a warm-up time, and then continue running the simulation for another 100 hours as the simulation time, And then report what happened. And obviously simulation will report to us what happens in the second hour, 100 hours, the simulation time. Okay. So, but as we just talked about, the question is that should we do this only once or more than once? So, one option is to run this simulation for multiple replications. So, for example, for replication 1, this is my setup. Okay. So I run another replication, replication 2. I do the same thing. I run the simulation, I let the first 100 hours to be the warm-up time, and then I consider the second 100 hours to be the simulation time. So the simulation will tell me how many parts can be generated with this setup in 100 hours. And maybe I can continue that all the way till I get to maybe replication 10. And then, so that will be another simulation run. Again, the first 100 hours will be warm up. The second 100 hour would be simulation time, and simulation will tell me how many parts are generated in the second 100 hours. And then at the end, simulation will report to me the average of number of parts that are produced in 100 hours across all these 10 replications. Okay, so the simulation will report the average of these numbers and all those confidence interval and standard deviations and so forth. Okay, so that's definitely one way to deal with it. Let's go and implement that one. So we can go to the simulation and just say, okay, consider the first 100 hours as warm-up time, then continue running the simulation for another 100 times, and just do that for 10 replications. And at the end, report the average of the number of parts that have been produced for these 100 hours of simulation runtime. Okay. Okay, so now I can see the result of all these 10 replications. So I can see the replication results, and it also shows me the average of the number of jobs that have left the system and a 95% confidence interval. Again, by going to statistics, you can here check whatever you want to show. Maybe I want to show average, standard deviation, 95% confidence interval, and so forth. Okay, so by going to statistics, you can check what you want to show. So here, if I want to report to my manager that how much parts can be produced in 100 hours in this manufacturing setting, I don't run the simulation only once and just say, oh, about 5,096 parts. Okay, so I run the simulation in 10 replication. That means 10 sample. Each sample is 100 hours. I look at how many parts can be produced in each one of these samples. And at the end, I report the average of these numbers and maybe a 95% confidence interval. And that number is much more reliable than running the simulation only once. Okay? But the other, there is another method too. Okay? Before we go to the other method, let's go to the variable. And here also we can see the average value for the working process. So that's average across all those 10 replications. Okay. So here also I can ask for a 95% confidence interval of working process. So if I ask you report the average working process and 95% confidence interval for working process for how given that we are running this, or we are letting the manufacturing operation to run only for 100 hours, so make sure that you come here and then you check the average and 95% confidence interval so that you can get the average and 95% confidence interval for working process as well. So that means on average there are about 19 parts on this manufacturing floor, and with 95% chance this working process average 19 is somewhere in this interval. So it falls somewhere between 17 to 21. So obviously every time we repeat the sample, so if I look at more 100 hours of operation time of this manufacturing process, so the numbers here, the numbers I get maybe if I look at another 100 hours of operation, replication 11, replication 12, the numbers I observe are a little different. My average would be different, right? So the average working process would be different. So basically here I says on average is about 19 parts, but with 95% confidence or chance, this average will vary between 17 to 21. So you want to report all these numbers to your manager so that they can know what is the average and how much variability it has, so that they can know how reliable this 19 point for working process is. Okay. So that's one way to run the simulation. What is the other way to run the simulation? The other way to run the simulation is to say that, okay, run the simulation for 100 hours of warm-up time, and then run the simulation for 1000 hours straight. Okay, and then after you run the simulation for 1000 straight, instead of reporting the results for 1000 hours, instead of reporting how many parts were produced in 1000 hours, just divide this 1000 hours into 100 hours. So run the simulation for 1000 hours, but instead of reporting everything for 1000 hours, cut this 1000 hours into 10 consecutive 100 hours, and then report the results for each 100 hours for me. Okay, so why this method also makes sense? Because when I get rid of the first 100 hours of warm-up time, I get to the equilibrium or steady state, and then I continue running the simulation for 1000 hours. After I'm done, let's say here. So this is pretty much the same. After I'm done with the first 100 hours, right, the simulation is in equilibrium. The simulation is in a steady state already, right? So I go back here and just continue running the simulation for another 100 hours. And I ask the simulation to report the results for the second 100 hours for me. So I don't need to assign any additional warm-up time anymore. The warm-up time is already over. I'm already past the initial part of the simulation. I'm already in this equilibrium or steady state. Run the simulation for the first 100 hours and then continue running the simulation for another 100 hours. So I'm already in the equilibrium or steady state situation. So, and then after that, I will continue again running the simulation for another 100 hours. And then I continue running the simulation for another 100 hours. And then I continue that all the way till I get to the 10th 100 hours. Okay, so this is pretty much equivalent to running the simulation for 1000 hours straight. So when I run the simulation, I just do the warm-up once, I get rid of that first 100 hours, and I'm already at this point, at the start of this at the start of the red mark, I'm already in the equilibrium point. So when I run the simulation for the first 100 hours, I am in the equilibrium or steady state point. So I'm good to report the results for the first 100 hours. When I continue running it for another 100 hours, I'm already in the equilibrium point. So I'm good to report the result for the second 100 hours and so forth all the way to the last 100 hours. So and why we are good to do that? Again, just because manufacturing process is a continuous process. So when I come back the next day, I just continue from where I left off the day before, and that's just another 100 hours of production in the equilibrium status. Okay, so and that's basically is going to give me a result which is equivalent to what I obtained using the first method. The advantage of this second method is that I don't need to run the simulation for warm-up time 10 times and get rid of that 10 times. So if you remember, if you can see in the first method, for each replication, I run the simulation for 100 hours and get rid of the warm-up time. So for 10 times, I run the simulation for 100 hours and get rid of the warm-up time. That's a lot of simulation time that we have to just waste, right? But in the second method, I just run the simulation for 100-hour warm-up time once. I get rid of that. I get to the equilibrium or steady state, and I just continue running the simulations for 100 hours. Okay, so what we want to see is that how I can tell the simulation to run the simulation for 1000 hours, but divide this into 10 100 hours and report the results for that. So each one of these 100 hours are basically what we call batch mean. Okay, so let me go to the simulation option here. So here basically what I want to say is that run the simulation for the first 100 hours. That's my warm-up time. Get rid of that. Then continue running the simulation for 1000 hours. However, batch mean. Here at the output reporting, just check the batch mean option. What is the length of the interval or the length of those little batches that we want to pick? Each one of them is 100 hour. Okay, so here in the batch mean, you have to put HR for hour. Otherwise, you get results that do not make sense. So click on the batch mean. Make sure you put HR next to 100 hours. That's a must. Otherwise, your numbers do not make sense at all. So this way, we tell the simulation that run it for first 100 hours. That's my warm-up time. Get rid of it. Then continue running it for 1000 hours. But instead of just reporting the results for just 1000 hours all at the same time, divide this 1000 hour into 10 100 hours. So when my interval length is 100 hours, obviously this 1000 would be divided into 10 100 hours, and then report each one of them as one replication. So if I go to the first one, I can just get rid of the replication because replication here doesn't mean anything. So we are using the batch mean method, and I want the length of this every little interval to be 100 hours. Again, don't forget to write HR here, otherwise your numbers do not make sense. So let me run the simulation. Okay, so after running the simulation, this is what I get. So basically I have 10 replications. So from replication 1 to replication 10, each one of them is just 100 hours of the manufacturing process, and it tells me how many parts have been produced in each 100 hours. And again, when I go to statistics, I can check to report the average of these numbers as well as 95% confidence interval. So this number, the last one is the average, and the other two are 95% confidence interval. It should show you the header of the rows, but as you saw, after I checked the 95% confidence interval, the last two rows were generated. So this row is basically the average across all the 10 replication, and this is the lower bound of confidence, 95% confidence interval, and this is the upper bound of 95% confidence interval. Okay, just make sure when you report your numbers, these average and 95% are not checked. Otherwise, you see more than 10 rows in the initial results, and it may confuse you. Okay, so this is the new average, lower bound of confidence interval, and upper bound of 95% confidence interval. And this is, as I said, pretty much is the same as previous method. And similarly, if I wanna report the working process, I can just come here and say that instead, in addition to the average, report the 95% confidence interval as well. So if I then ask you, what is the working process for 100 hours of manufacturing operation? You say average is 21, and it's between, the lower bound of 95% confidence interval is 18, and upper bound is around 24 parts. Okay, so So that's just another method for running non-terminating systems. So again, either you run it for multiple replications, but in each replication, make sure you assign the warm-up time, because each replication you start from 0 part in the system. So you have to get rid of the warm-up time in each replication, okay? And then continue running the simulation for whatever time you want. Or the second method, just run the simulation once, get rid of the warm-up time, and then continue running it for longer time. And then you can tell the simulation to divide this longer time into smaller intervals for you, and report the results for each one of these intervals. And we call them batch mean. And the advantage of this method is that you run the simulation for warm-up time of 100 once, and then you get rid of that time only once. So the simulation time is supposed to be smaller than the first method, when you run the simulation for 100 hours of warm-up times 10 times, and you get rid of that 10 times. Okay, so just make sure you're familiar with these options and how we should change the setup, the simulation option window to implement any of the methods. Just again, as I said, in the batch mean, when you choose the batch mean of 100 hour, make sure you type hour, otherwise you get wrong results. Okay, guys? So that's basically the whole concept of terminating systems. Non-terminating systems.